Okay. The power rule. The power rule looks like this. Now, what we do, or what a mathematician would have done, is they would have said, well, let's take out our definition of the derivative, and let's do all 6 of these. Now, if we decided to do that now, we would take the next half an hour to show all of that work. So instead, we're going to pretend that we did that and say, okay, I did the first one, and I got 2x. I did the second one, and I got 3x squared. The third one, if you had to do the x plus h with the power of 4, right, you'd have to expand that all. That would take some time, okay? Or pretend that we did that, simplified everything, factored out the h, and applied the limit, and we get 4x cubed. And after doing a couple of these, what normally happens for mathematicians is that they start to see a pattern. They say to themselves, hey, wait a minute. If I notice a pattern, and this pattern always works, then wouldn't this be much faster than always using my definition of the derivative? And the answer is yes. So you might be noticing a pattern so far. See if what you think of your pattern works even if there's a number in front. With this number in front, this one would become 9x squared. So do you see how the pattern works even with the number in front? What about a negative exponent? This one wouldn't be very much fun with the definition of derivative. Another negative exponent. And so we do a bunch of these, and we start to recognize there's a pattern happening. In each of these ones, it seems like the exponent is coming out in front of the number, and then we're subtracting 1 from the exponent each time, even with the negative. The exponent -2 came out in front. Subtracting 1 from -2 would get us to -3. And one of the things you're going to get really good in calculus is subtracting by 1. This is like a skill you're really hoping to get good at. You will get really good at subtracting by 1 in all sorts of matters, even if we had stuff that looks like it doesn't fit this pattern. It does. For example, in between here, what's another way that I could write square root of x? I could write square root of x as x to the half. And then does the pattern work with fractions? Yes. The 1/2 would come out in front. You would subtract 1 from 1/2. Like I said, you'll get good at subtracting by 1, and you get -1/2. Does the pattern work with just a number without an x? Well, yes. You're going to probably learn that anytime you have a constant, that the derivative is 0. But if you thought of this as 5x to the 0, when that 0 comes out in front, it would make the whole thing 0. And it works for this one as well. If you have 7x, that's 7x to the 1. If you bring that out in front, again, you're going to learn to just write 7. But you could write 7x to the 0, which is going to be 7. When I subtract that 1 from the exponent, I get an x to the 0. Even with cube roots, rewrite this one would be 1/3, so that 1/3 would come out in front. I'll let you do the mental math first. 1/3 minus 1. How did you do? And then here we have a square root on the bottom. We have to use a couple of exponent laws. The square root on the bottom would be like an x to the half on the bottom. This rule seems to only work when you have an x to the some sort of power at the top, whether it's positive, negative, fraction, or whole number. And so having a power on the bottom bottom of your fraction, you can use your negative exponent rule, bring it to the top of your fraction, and now bring that 1/2 out in front, subtract 1 from your exponent. And I guarantee some of these last ones, like the cube root of x with the definition of the derivative, whew, I think that one might take us 10 to 15 minutes. We probably have to factor a cubic in a weird form in order to make it work. And so we have what is called our power rule, is the one that we've been using. Okay, so if you have a power, any exponent n, that n comes out in front, and you subtract 1 from the exponent. This works for all real numbers n. This is a short form for writing for all real numbers n. Isn't that weird? Okay, I love some mathematical. You've seen the real number symbol, right? That's a lot shorter than writing them all out. Okay, you've seen this, n belongs to the real numbers, but this upside down a, that means for all. Because mathematicians would find that writing 2, 3-letter words takes too much time. So we're trying to make things more efficient. So certain times when you have to write lots of words, if you have to write them often in proofs, then they start using symbols to make it even shorter. And here's one of those symbols. My favorite, probably not very many times in your lifetime you've really wanted to write if and only if, but there is a nice shorthand for that, if, which means if and only if. So if you wanted to write that, you could add that extra f to really imply this works if and only if you do this. Try anything else and it won't work. But if you do this, if and only this. Anyways. And here's the constant rule, which could be part of the power rule, but anytime you have a constant number and you take its derivative, it just becomes 0. That one's really easy. If we look at what would happen if you did this, how would this work? We would have f of x plus h minus f of x over h. And the top would be top would be 3 minus 3, right? You get 0. So the question is, why is this limit equal to 0? Because technically we still have 0 over 0. There's no way that we're ever going to cancel out this h. Okay? But if you came to h from the plus side and got really, really close, it'd be everywhere else, it's 0. No matter what value you have on either side, it's going to be 0. And as you get closer and closer then from the left side and the right side, it will be 0. But now we can just use the constant rule. And once we develop these rules, we just use them. Now, when you guys go into university calculus, chances are you're going to learn the limits unit first. And you're going to learn the definition of the derivative. And you will already know there's a shortcut coming. So you're like, this is going to get easy. But everybody else who's only taking grade 12 pre-calculus class, who's in that class, is like, their eyes are like, how am I going to do this all semester? This seems really complicated. And you're sitting back and going, it's going to get better, it's going to be fine. In fact, you will have a tough time sometimes with the definition of the derivative questions because you will know the answer before you even start the question. And you'll be like, oh, to show all this work just to get the right answer. But you know that it's coming, that it's going to be shorter. The other thing that professors will do once you get to university is they will show you the proof for why this works. Okay? This is something that happens in universities. They don't like giving you a rule without giving you the long-winded mathematical proof. And often, they're very hard to follow, and there's a lot of little bit of hand-waving in between or really complicated notation. And then that also scares people. You have to realize, okay, it's okay if I don't completely understand the proof, because afterwards, once a mathematician has proven it for you, they feel vindicated that they're like, okay, you guys all got that, right? And the whole audience goes, no, we don't get that. Okay, but we'll pretend you got that, and now we can use the shortcuts. And so now we have our first shortcut, which is the power rule. We have the constant rule, and the power rule, if you have a number in front, well, that number in front really doesn't matter. You can just apply your derivative to that as well. And we saw that with, right, we did y equals 3x cubed. Technically, when we go to the derivative, this is saying, just do the derivative of this, which is 3x squared, and then 3 times 3, well, that gives you 9. But you are going to immediately go from here to here, because you're just going to imagine that 3 is coming out in front. It's hitting the 3 that's in front, so 3 times 3 makes 9. Subtract 1 from the exponent. And you will not think of this derivative rule any different than the normal power rule. Just the number in front, oh, it's still the power rule. It acts the same every single time. So now we get to do questions, and calculus is like, almost like going back to grade 9. I think it hasn't probably been since grade 9 that you get math questions where you just look at them and write the answer. Right? Sometimes in grade 9, your assignments are like 50 questions to do. And you can get them done in like 7 minutes. In grade 12 pre-calculus, if I gave my class 50 questions to do, they're like, what? I don't have time for this. I'm supposed to sleep tonight. But we get back to that in calculus where we are just going to, for almost this entire unit, most of this unit is see a question, write down the answer. And it's kind of refreshing to get into that. And the other nice thing about it is that the rules, if someone else is like looking over your shoulder, unless you know the rules, it's kind of hidden. And it looks impressive. They look and like, how did you get that? And you're like, I'm not telling you. Right? You can just let it be impressive the whole time. Okay? Differentiate this one. This is a medium level one because the power rule only works if your power is in your numerator. This x to the 8 is at the bottom. So what we have to do is first move that to the top of our fraction using our exponent rules. And another nice thing about this course with calculus, your algebra skills are going to get great. You're going to really revisit all of your exponent laws and get good at them again. So the course does a great job of reviewing all the things you already know or should know, get really good at them, and then apply them here. Now, what am I going to do? I'm going to bring this 8 out in front. That would make negative 24. Subtract 1 from the exponent. Subtracting 1, I said you're going to get good at it. You're going to be tempted to do x to the minus 7. Can you see yourself taking a moment off? And when you subtract 1, write x to the minus 7 instead of x to the minus 8. And here, you could read, I could reduce that to negative 6x to to the negative 9. So notice the notation that I almost screwed up on because I was thinking ahead. When we're writing out the equation, that's when we're using y equals. When we take the derivative, you have choice. You can write y prime. You could write dy dx, Leibniz notation. If the question started in function notation, f of x, you would probably write f prime of x. But it's not wrong to switch between them. But there are sort of some protocols. If you had y, you would choose one of these two notations. You probably wouldn't write f prime of x because you didn't have f of x to begin with. And what you'll see in these questions as we go through them, I try to introduce as many different types of notations that you could possibly see in university or in different textbooks, just to get used to it. Here is another way of asking the derivative. It says find d dx. This, like, the derivative is dy dx. If y equals 7x to the 4, can you see that this is like this? This is dy dx. It's just hidden in the notation a little bit. So when you have a d dx, it means find the derivative with respect to x. So the dx on the bottom is telling you which variable you're doing the derivative with. Because you could have an equation instead of the variable x, you could have the variable L. Then you could have a d dl. It would just feel a little bit weird because we get so used to dy dx, but you could have a dv dc or whatever letters you would like. So the derivative in this case would equal, bring the 4 out in front, subtract 1 from the exponent, and that is what you would get. And this is about as hard as they get. We've got radicals, which you have to change with your exponent laws, and you have x's on the bottom. So I would start by changing that cube root to a 1/3. And I'm perfectly fine if you know that that would be x to the 2/3 right away. Okay? But I'm just showing it really technically means x squared to the 1/3, a power to a power. You would multiply those exponents, so you would get x to the 2/3. And now I'm going to take another step, and I can move that 2/3 to the top with my negative exponent. And this is the hard one. So that was the hard step. We had to do a little bit of rearranging to get that power to the top. Now our derivative in one step, bring the negative 2/3 out in front. Well, negative 2/3 times 7/3 would be negative 14 over 9. Subtract 1 from your exponent, and you would get negative 5/3. But not too bad. This is a good one, though, to reflect upon and imagine the definition of the derivative. So the definition of the derivative, right, you would have to do the limit as h goes to 0. You'd have h on the bottom, and you'd have to plug in x plus h where the x is. So on the bottom there, you'd have x plus h. It'd have to get squared. You get x squared plus 2xh plus h squared inside a cube root minus f of x. And you would have to simplify all those square roots and cube roots using difference of cubes and sum of cubes and factoring to eventually try to get that h to cancel out. And because of our pattern, we're able to do it in one step. Seriously, this one would probably take 15 minutes before you felt like I should give up. And then, now it's like 5 seconds. It'd be so nice if there was something like this in English for essays. Like, here's your 20-page essay. What's that, gonna take you a week? Well, I guess they have that now. That's that IA thing. You just go onto the internet and say, write me an essay about Macbeth, and it's done. So good. So bad. I think the difference here is you're actually still doing this. There's things for math too, right? You take a picture of something, it gives you the right answer. Not very helpful for you later on, but yes. And then we could think, hey, let's work backwards. If I told you the derivative was 5x to the 4, can you imagine what you had started with? Give you a second. All right. How'd you do? Pretty good. You can check it. You could take the derivative. The 5 would come on in front. Perfect. Subtract 1 from the exponent. So now we just move things backwards to what we originally started with. Ooh. So for something like this one with the number out in front, first of all, you would know that to have the x squared, originally, you would have needed an x cubed. What number would have had to be in front then to get the 12? There would have to be a 4.